Hey everyone. So today is lesson 2 in derivatives. And yesterday what we focused on was, okay, let's make the connection between derivatives and finding the slope of a tangent, taking the limit, using the limit to find the slope of a tangent is calculating a derivative, okay? Now, one of the things you would have noticed about looking at it from a limit perspective is the questions are rather long. There is a lot that you have to do when you're using first principles, okay? And so the next couple of lessons, as we shift the conversation less from first principles, less from a limit perspective and more from just a derivative perspective, we want to look at, are there ways we can not always have to use limits to figure out the derivative of something, okay? You can always use limits to figure out the derivative of something, okay? That'll never change. But if there are certain ways we can get to the derivative quicker than using a limit, then that would be helpful for our questions, okay? So today we're going to learn the first of a few of these different ways, and it's going to look at something called the power law. Okay, so we know that to find the slope of the tangent at any point on the curve, we can use first principles. First principles, there are two options with first principles. You could do the limit as x approaches a of f of x minus f of a all over x minus a, or you could do the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, method 1, method 2, both of those are first principles. Okay, for example, and this is all in your notes, so you're just kind of reading along. For example, to find the slope at any point x, so now notice it says the slope at any point, so we're trying to create that general formula right now. Which is the derivative equation that we started talking about yesterday, right? Remember how yesterday we were graphing the original function and the derivative function? So that's what we're looking for here. When they say the slope at any point, we're just looking for the general equation. So what we would do is we'd use first principles. So we're saying that the derivative of x, here, let me hide myself for a sec. The derivative of x is the limit as h approaches 0 of f of x plus h minus f of x over h. So then my equation was 3x squared plus 7. So I plug in x plus h for x, and I plug in x for x. Okay, I'm going to have to do the math here. So x plus h all squared would be x squared plus 2xh plus h squared. Throw the 3 into everything. When I throw the 3 into everything, I would have, I'd be down to this pink section now, and now we're going to use algebraic skills to simplify. Again, the reason we're simplifying right now is because I can't plug h as 0 into the equation directly because of that h on the bottom. So I go ahead and simplify. My 3x squares are gone. My 7s are gone. That allows me to factor out an h. When I factor out an h, I end up with 3 times 2x plus h. I can now plug h in as 0. So I'm going to do that, and I get out 6x. So my derivative equation is 6x. Okay. Now, all of that should sound very, very familiar with you. With you is probably a bad preposition there. Probably should have been to you, but whatever. Okay, so now what you're going to do is we're going to take a look. In most cases, we want the slope at a particular point. So that 6x that we just did, that was the derivative equation that was representing all the slopes at any given point. But now we want to find a specific slope at a specific point, and that specific point is at 1, 10. So all we do is we take our derivative equation and we plug in 1 for x, and we get out 6. So at x equals 1, if I wanted to draw a tangent line at x equals 1 for the original f of x equals 3x squared plus 7, the slope of that tangent line would be 6. Okay? Okay, this is a long and tedious process. Surely there must be an easier way. Form a group of 4 people or so, and each person will choose 2 or 3 functions from the list below and use first principles to find this derivative. Now, from watching this on YouTube perspective, obviously you're not going to get into groups, but what I am going to strongly encourage you to do, and I mean, it's up to you how you want to handle this, but these are 8 things that I'd like you to find the derivative to, okay? These are great review questions for how to find the derivative using first principles. Just because the next week or so is going to show you some shortcuts, you will still have to use first principles. You will still, like, there will be test questions where we say solve using first principles. And if you don't, if you can't speak to me in the proper calculus language and use first principles, you won't get any marks for that question, right? So obviously, I'm not going to give you time to do this right now because you can press that little pause button. Go ahead and press that little pause button. I'm about to show you all the answers, but it would be really good if you could try them all, actually. Take some time, use this as a nice review, and find me all the derivatives. Press pause for me and go ahead and do that. Welcome back. It's like you never left. Okay, so here are all the answers. And now what we want to do, you can check yourself, but what we want to do is we want to try and look for patterns of how I go from the original function to the derivative, okay? So how do I go from 3x squared plus 5 to 6x plus 5? Well, for some of you, that 5 may have been the first thing that caught your eye, okay? Take a look at this. This 2x went to 2, okay? Interesting. So let's take a look at the first term. How could I go from 3x squared to 6x? Well, actually, I could take the 2, multiply it by 3. That would give me 6, right? Does that work on the other side? Oh, well, it's still 2 multiplied by 3 there. So that actually did work, okay? And then what I want you to notice about the degrees are actually going down 1 for each term. So this was a degree 2. Now it's a degree 1 over here, okay? This was a degree 2, now it's a degree 1. If you looked at 5x was degree 1, and now it's a degree 0 because there's no x there, okay? So what's happening? Based on your results, a rule that makes finding the derivatives oh so much easier than using first principles would be the following. Each term will go down a degree, and the original exponent gets multiplied by the original leading coefficient, okay? So if we looked at f of x equals 2x plus 4, okay? This right now has an exponent of 1. So if I went 1 times 2, that's just going to give me 2. And then this drops to x to the 0. So that would just give me 2. And then this guy's gone. The constant term will drop off. So we'd just be left with 2 there. The derivative of f of x would be 2. Okay. What about for 5? I'll take that ink off for you, sorry. The derivative there ends up being 0. Okay, just for the exact same conversation that we just had. Okay. So in general, the power rule states if f of x equals x to the n, then the derivative will equal n times x to the n minus 1. So essentially, again, what I'm saying is every term, this guy goes to the front and gets multiplied by anything that's there, and then that guy drops a degree. That's where the n minus 1 is coming from, okay? Okay, so now that we know a simpler way to determine derivatives, go back to the previous section, that table that you did, and use the power rule to determine the derivatives. Okay, so we're just going to go back and check them. I've already talked about the first 2. So we're not going to talk about the first 2 again, but let's just take a look at a couple of the other ones here. For instance, let's look at this guy, f of x. Sorry, I'm trying to get my ink on and I'm doing a horrible job. Okay, so that's the same as saying x to the 1/2, right? The root of x is the same as x to the 1/2. So look at what happened. The 1/2 came to the front, and then my degree dropped 1. Okay, so x to the negative 1/2 came from 1/2 minus 1. 1/2 minus 1 is negative 1/2. Okay, let's take a look at this guy, this f of x. So we could look at that as 1/2 x to the -3. Okay, well, the -3 comes to the front to get multiplied. 1/2 times -3 is -3/2. Look at that. Okay, and then if -3 drops a degree, -3 dropped a degree would be -4. Okay, and it works for every one of these guys. This guy would be x to the -2. -2 comes to the front, and then -2 drops a degree to get me my -3. Okay, when I have multiple terms, I just do that to each term. So the 2 comes to the front, that's where the 6x is coming from, -5, and then the constant term drops off. Okay. This guy here, that'll end up being 12x squared right there, constant term drops off. And this will be x to the -1. The -1 comes to the front, that's where I get the negative right here, and then -1 dropped a degree would be -2. Okay, so it works for every one of those guys. Cool. So find the slope of the tangent line to the graph g of x equals x/3 to the 5 at x equals 2. Well, the first thing I'm going to do is find the derivative. So I need you to look at this as, this is like x to the 5 over 3 to the 5. Okay, so x to the 5 over 3 to the 5 is the same as saying 1/243 x to the 5. Okay, I have not taken a derivative there. I just kind of separated out my variable. Again, 3 to the 5 is 243. That's where the 1/243 is coming from. Okay, now if I follow the power law, oh, sorry, I don't know where that went. So this is going to get multiplied by 5. So it'd be 5/243. And then my x term drops a degree. So that would end up being x to the 4. So I have 5/243 x to the 4. This represents the equation of the derivative. Okay. So that represents the equation for all slopes, right? That would be the one I would graph with the original function like we did yesterday, okay? Now, it says I want the specific slope at x equals 2. Well, how do I do that? I just plug in 2 for x and solve, okay? So if I plug in 2 for x and solve, I end up with 2 to the 4 is 16. So I end up with 80/243. Okay, so what did we just do? We just said if, I just want to clear the ink I have, if we graphed this guy and I wanted to create a tangent line at x equals 2, the slope of that tangent line would be 80/243. Okay. I know I've been saying that over and over and over again, but I really want you to have a picture. I don't want you to just work blindly with numbers. I want you to have a picture of what we're doing and why we're doing it, okay? It still all connects back to I'm trying to find the slope of a tangent line, okay? All right, so the distance in meters above the floor of a particular basketball player is described by the function s of t equals -4.9 t squared plus 5t, where t is time in seconds. Remember, the slope of the tangent for a distance or position versus time function is the instantaneous velocity. So this s of t is the this s of t is the position function. If I was to find the derivative of that, the derivative would represent the instantaneous velocity, okay? And we've done a couple questions like that where we're making that connection. Okay, so determine the player's hang time. That is the total number of seconds that the player is in the air. Okay, the total number of seconds that the player is in the air. Okay, well, how are we going to do that? First thing we're going to do is we're going to figure out the derivative. So if I go to figure out the derivative, the 2 got multiplied by the -4.9, and then I dropped a degree. So the velocity function is -9.8t plus 5. And how did I get the velocity function? I took the position function and took the derivative of it. The derivative of your position function is your velocity function, okay? Okay. Now, I want to take that velocity function and plug in 0. Now, if I'm plugging 0 in for the velocity, I want you to think about what I just did. Where in this graph would the velocity equals 0? So remember, the velocity represents all of the slopes of the tangent lines, right? For the original position function. So think about the original position function. Let me even draw one for you for a sec. Let's just say here is my basketball guy. Here's his jump, and there he lands. Okay. Where would I end up having a slope of 0? I would end up having a slope of 0 right there. I have a velocity of 0 the second I'm changing direction. Right? There is this moment in time where I am not traveling up and I am not traveling down. There's this instantaneous moment where my velocity is 0. I'm not moving. Okay? So if I can figure out that point, that's going to tell me the t value it takes to get to that point. Okay? So that'll tell me that amount of time. Now, is that the full hang time? No, that's only half the hang time, but we're getting there, and we're getting there from a calculus perspective. So then once we have half the hang time, we can multiply it by 2. Okay, so why choose 0? If the velocity is 0, we are at the max, the point where we turn direction. Okay, so that gives me t is 5 over 9.8. Okay, I'm just solving that, bring my 5 over, divide both sides by negative 9.8. Okay, but now we want to multiply that by 2 for the total time. So the total time is 1.0204 seconds. 1.0204 seconds. So the player is in the air for just a little over 1 second. Okay. All right, question 2. Determine the player's initial velocity. The initial velocity, that would be at time 0. So I take my velocity equation and I plug in 0 for time. That gives me 5. So the initial velocity is 5 meters per second. Okay, determine the player's vertical leap. That is the maximum distance of the player's feet above the floor. Well, the maximum distance is right here. Again, I want to make the point. You guys have done questions like this in 20-1 with quadratics, okay? The point is not to answer this from the mind frame of a 20-1 kid. The point is to answer this from the mind frame of a calculus kid. You must approach this using calculus concepts now that you're in a calculus class, okay? So determine the player's vertical leap. Well, I already know the time frame at the max. So if I know the time frame at the max, I just plug that in to my original position function. And that's going to give me 1.28 meters. Okay, so the maximum distance of the player's feet above the floor is 1.28 meters. I would call that fairly high. I could not jump a meter in the air. Sorry, I turned because I wanted to look. There's a door right there, and a door post or a doorknob is 1 meter high. So go look at a doorknob and ask yourself if you could jump just, higher than a doorknob. I can't, I'll be honest. Okay, sketch a graph of the player's height and velocity as a function of time. So the height is your original position function, and the velocity is your derivative function. Okay, so go ahead and do that. Maybe pause me, and then you can compare my drawing with your drawing. Okay, and you should have a picture that looks something like this. Okay, awesome. So today is all about just getting comfortable using this power rule, the power law. And again, when you're finding the derivative using powers, your exponent comes to the front. For every term, the exponent comes to the front and gets multiplied by the coefficient that's there. And then whatever degree that original term was will drop 1 degree. Okay, that is the power law. Okay, so that's it for this guy. This gives you some time to practice, and your homework is listed there, and connect with me if you have any questions. Okay, take care, guys.